So, how does science actually move forward? We like to imagine it's this clean, straight line of progress. But the reality? Oh, it's way more chaotic and human than that. So, how do we, as scientists or even just curious people, know when it's time to let go of a perfectly good, comfortable old idea for something new and, well, kind of scary?
The great physicist Max Planck, man, he didn't mince words. He basically said that new ideas don't win by changing people's minds. They win because the people with the old ideas eventually aren't around anymore. It shows you just how fiercely people cling to what they know. It's a real battle of worldviews. And that brings us to the big question, right? If even these brilliant scientists get stuck in their ways, how does science as a whole ever move forward? How does it pick a winner between an old, trusted theory and a radical new one? Is there a better way than just waiting?
Okay, so here's our game plan. We're going to start with this core idea, the principle of least surprise. Then we'll see it in action, first by rethinking motion, then by rethinking heat and information. After that, we'll zoom out and see how this connects physics to, well, pretty much everything. And we'll end by asking, what's the next big surprise waiting for us? It turns out the answer to our question comes from this really elegant idea from statistics and information theory. It's called the principle of least surprise. And it's a surprisingly simple but really powerful tool for figuring out which of two ideas is probably on the right track. To get it, we need to understand this one key ingredient called surprisal. Just think of it like a shock meter for your scientific theory. When your model sees a new piece of data from the real world, the surprisal is just a number that says how shocked it is. A low number is like, yep, saw that coming. A high number is like, whoa, hold on, that was not supposed to happen.
Let's make this real. You toss one coin, it comes up heads. Your model of a fair coin is not surprised at all. The surprisal is super low. But what if you toss 20 coins and they all come up heads? Now your model is screaming. The surprisal is through the roof. It's so high that you'd have to start thinking, maybe my model is wrong. Maybe this coin isn't so fair after all. And that's the whole point. So the principle is basically this three-step dance. 1, you gather up all your data, everything you've observed. 2, you take your competing theories, the old way and the new way, and you see how surprised each one is by all that data. And 3, you pick the winner. And the winner is the model that is consistently the least surprised. It's the one that gets a quiet little nod of approval from the universe. All right, let's put this idea to the test. And what better place to start than with one of the biggest scientific earthquakes ever, Einstein's theory of relativity. For a while, there were a couple of ways to think about it. Let's see which one the universe is less surprised by. The old way, which, to be fair, is where even Einstein started, is a real headache. You're trying to juggle two different points of view at once, each with its own rulers and clocks, and it just gets messy. The new way, the metric-first approach, is way cleaner. You just use one single map of spacetime, and you only have to track the traveler's clock. It's simpler, it's more intuitive, and, as we're about to see, it's a lot more powerful. And bam, here's the payoff. When you throw reality at these two models, the old way gets surprised over and over again. It struggles with simple things, and it completely falls apart as soon as you talk about acceleration or gravity. But the metric-first model? It handles all of it. No problem. It is just consistently less shocked by how the universe actually behaved. And here's the really crucial part. By picking the simpler, less surprised model, we didn't just get a neater way to do math. We got a model that unlocked the door to Einstein's masterpiece, general relativity, our theory of gravity. The better idea wasn't just better, it was more profound. It pointed the way forward. Okay, so that was motion. Now let's jump to a totally different field and see if the same logic holds up. We're going to thermodynamics, the science of heat and energy. And here, the big shift was from seeing heat as just, well, heat, to seeing it as information and choices. And what do you know, it's the same story all over again. The old 19th century ideas about heat were constantly surprised. They couldn't explain entropy, they got totally confused by weird stuff like negative absolute temperatures, and they sure as heck had no idea how you could get complexity from chaos. But the new entropy-first model?
It explains all of these things, no sweat.
And this forces us to update our idea of entropy. You probably learned that it just means disorder, right? But that's kind of fuzzy. A much better way to think about it is as the average surprisal. It's a direct measure of how many different choices or states a system could possibly be in. More choices, more entropy. Simple as that.
So, what makes this new view so much better? This quote from the source material just nails it. The entropy-first approach doesn't just hand you the laws of thermodynamics and say, here you go. It tells you why those laws work and, just as important, when they work. It's built on the deeper, more fundamental ground of probability and information. So, just like with relativity, the lesson is clear. A model that's based on a deeper, more fundamental concept, in this case information and choice, is way less surprised by the rich, weird, complex universe than the older model that just stayed on the surface. Okay, now I want you to buckle up, because this is where things get really mind-bending. This whole idea of picking the least surprised model, it's not just for physics. It's a universal key that unlocks connections between fields you would never think are related. And it all comes down to the power of correlation. So this net surprisal idea, it actually has a technical name. It's called Kullback-Leibler divergence, or KL divergence. It's the mathematical engine driving this whole principle. But what it really is, fundamentally, is a way to measure the hidden connections, the correlations, between a model and reality. And why is that a big deal? Because it's universal. I mean, look at this. The exact same mathematical idea is the thread that connects all these different fields. It's what lets us calculate the work an engine can do. It's how we analyze the information packed into our DNA. It's how ecologists model animal behavior. It's even the secret sauce behind the AI and data compression on your computer right now. It's everywhere. And if you want one number that just shows how deep this connection is, get this. The paper calculates that a single nanojoule of work, a tiny amount of energy, at room temperature, can generate over 44 gigabytes of information. That's not a metaphor. That is a direct mathematical bridge between energy and information, all built out of this idea of surprisal. It's wild. So where does all this leave us? We've seen that this principle of least surprise isn't just a neat trick. It's a powerful lens. It gives us a rational way to choose better ideas, not because of who's shouting the loudest, but based on which idea is simply less shocked by the evidence. And that really is the biggest takeaway here. The best ideas in science aren't just right. They're humble, they're robust. They're the ones that are the least shocked when we discover something new about the universe. They win because they explain more elegantly and more deeply. Which leaves us with one final, and I think kind of provocative thought to chew on. If this principle is as powerful as it seems, then progress never really ends. So, what piece of settled science from our time is secretly just waiting for a better, less surprised idea to show up and completely change the game all over again?